Now, a key property of the Laplace transform that makes it useful for solving differential equations is how the transform behaves when you apply it to the derivative of a function. So here we suppose that we have a function little f, which has a Laplace transform capital F of s. And then we're going to see how we can express the Laplace transform of the first derivative of the function f. Well, applying the definition, we see that this is the integral from 0 to infinity of e to the minus st times the derivative df dt. This integral takes place with respect to t. Now, this integral is set up and ready to adapt using the technique of integration by parts. So this would be the product e to the minus st times f of t evaluated at t equals 0 and infinity. Then we would subtract the integral from 0 to infinity of the derivative of the exponential term from the original integral, which is minus s e to the minus st, taking its derivative with respect to t, of course, so this would give us e to the minus st multiplied by minus s. And then this is multiplied by the function f of t with respect to t. Now, okay, so first we evaluate these limits here, and as usual, because f has a Laplace transform, the limit when we substitute in t equals infinity, when we take the limit of this expression here in the bracket as t tends to infinity, we get the value 0, because the exponential term dominates, okay, and that tends to 0. Then we subtract what we get when we substitute t equals 0 in here to this expression, and that will give us e to the 0 times f of 0. So in other words, just f of 0, the initial value of the function f. Then over here, taking the factor of minus s outside of the integral will give us plus s times the integral from 0 to infinity e to the minus st times f of t dt. There's minus f of 0 plus s. But what is this integral here that we're looking at? Well, this is nothing other than the Laplace transform of the function f itself. And this is the required result.